Thanks for being here. So, unfortunately, Karthikeyan, after the long travel from India, was not feeling well. So it's me only. So let's get started. Eventually, 1 kilobits is a huge value to speak. So let's speak another other way. So 1024 bytes. How to squeeze Zephyr under 1024 bytes. That's what we're gonna speak. So shortly about myself. Parthiban, I've been doing embedded software for like maybe 12, 13 years now, predominantly in the initial days with Linux systems and past 5 years with Zephyr as well. And I myself live in Berlin. And as part of Linumiz, we are actually embedded software servicing company in terms of providing software services for Linux and Zephyr, and primarily software consulting in this field. So in short note, what we're going to look. So what is the current state of Zephyr when we try to compile for a low footprint memory devices, how it look like, and how this memory layout is layered by default from the linkers and so on, and how can we analyze if we have a way to fit in under 1 kilobytes of RAM. So, and then like how do we manage to do it, let's say run simple applications like hello world, blinky, or finally with I2C applications, how we manage to do it under 1024 bytes. So little bit of an advertisement slide here. So when we started with Texas Instruments SoC, we actually currently having a collaboration with Texas Instruments directly for support for MSP-M0 family in the Zephyr upstream. So we've been working with them for like half a year in terms of getting other series of SoCs to the upstream Zephyr, which means like there are a couple of other series like G and L, and this specific series has been launched beginning or like March of this year. And in the quite of interim of what we are doing already in the upstream for Zephyr in MSP-M0 family. So the other families are like rich in a way. It comes with like 32 kilobytes of RAM or maybe at least 16 kilobytes of SRAM, and we already managed to port a large amount of other activities, let's say SoC drivers which is needed for it using the hall, and let's say devices system and all this thing which has already been upstreamed in one way or another, meaning not all of them, but at least we had quite a activity done in the downstream, and this was done and it was working fine for the other couple of series. So when this was launched, so why not, and then like we could try directly running under 1 kilobits of SRAM and figure out is it's really possible to do it on that. So that's the adventure. And then like one additional note here, it's like when we spoke about this particular talk with Texas Instruments, and they were happy in helping figuring out like giving few, let's say 10-15 samples of their SoC, and then we collaborated with another partner in India to get some free PCBs there. It's right over here, so please get it after the talk, after if you wanted to play around with this particular SoC. So now technically, so when it comes to 1 kilobytes of RAM, I started when immediately appeared in March. I was in Nuremberg for the embedded world and saw this particular small SoC, and then I looked into the Zephyr tree. Okay, see what is the lowest footprint currently Zephyr runs on. So that's results in like there are 2 kilobytes from ST and couple of them from RISC-V based WCH SoC, which has been recently added. And when we try to compile a basic applications like GPIO, blinking, or let's say hello world, it's almost like 95% of the RAM is gone, and then it still works, and the basic application still works. And if you try to do I2C or additional real use cases, doesn't fit in, and it still overflows afterward. So that's in like, okay, so that's the current status of it. How do we fit under 1 kilobytes? So this is just again, I'm going to skip this couple of slides. How do you do SoC porting on your when you do have a new SoC? And I will skip this slide because I think most of you people might be aware already how to port a new SoC into the Zephyr platform. So we added the SoC directory for CX series, that is the one with 1024 bytes of RAM which comes with. So when we add the device tree system board directory and try to compile off the shelf hello world, off the shelf blinky sample, so it overflowed by around, let's say, approximately 3000 bytes or like 4096 bytes when we enable some debugging or console logs and so on. So that doesn't fit directly. So that was the resultant of CX out of the shelf Zephyr compilation. So what we can do immediately to cut strip something which is possible to do it. So to okay, let's see. So how do we still use the same SoC to compile it, but try to still optimize it out, and then finally once we get to the final optimized value, we can run the actual SoC. So the one way we figured it is like, so fake the RAM in terms of the device tree itself, and let's say the compilation system doesn't aware, like once you flash it, it's really matters, but then during the compilation it doesn't. But so we fake it to, let's say, a larger value like 32 kilobytes or 8 kilobytes of RAM, and then the compilation system is happy just because it's awareing that like parsing the device tree itself is the only way it can figure out what is the memory in there. And there are set of low-hanging fruit where you can think of immediately optimizing the memory. This is straightforward, which is like, say, in the kconfig or in the device tree system, you disable the amount of peripherals you don't want it to have, or you don't want to try anything special. So except UART in Poland and Pollard mode, all the rest has been disabled by default as a low-hanging fruit, just to see if we can manage to run, let's say, hello world application in the nutshell. So otherwise, let's say the I2C and other peripherals, like basic peripherals on the serial buses, are completely disabled. And there is also one other optimization which you can technically do from compiler side. So this is again off the shelf, passing an option to GCC on behalf of the kconfig system. So when you do a size optimization, -OS will be passed, and if you wanted to have even more aggressive optimization in terms of the sizes, that would go to OZ. So what would be the difference? It's like, say, it would be creating a slower path inlining functions all of the areas, but then it wouldn't, it would technically help you reduce the size in terms of it. So that's the low-hanging fruit you can directly try without much of digging deeper into how the code looks and how do we optimize further. So after those optimization footprint, so we landed up something around still with faked 32 kilobytes. You can think the percentage you can ignore, and then the used size is somewhere around 1500 or let's say 1600 when we want to do some print K on top of it, or to see booting sequences in there. So that's the default low-hanging fruit which we figured out. And now comes the real squeezing effort to figure out under 1024 bytes. So one quick note about it, and there is this particular SoC is technically execute in place. Okay, so we tried seeing if it's possible to figure out a footprint, like what exactly happening when we disable XIP. XIP probably might aware, so means like the CPU directly fetches the instruction from the flash and runs in the CPU, and only matters to the RAM itself is the data section and processing of the variables and which you declare within the function scope or in the global scope. So otherwise, that's the scope, which is when you have XIP disabled, that were around like 8 kilobytes of RAM which you would require to run this nutshell. So that's just an information slide there. So now that we are under, let's say, 1500, 1600 bytes time, so how do we optimize the memory further to 1024 bytes? So we have a set of utilities which is part of Zephyr already, which you can technically use it to figure out where the memory goes and how do you identify which part of the memory can be basically optimized. So these are a set of tools which you can use it off the shelf. Let's say these are all part of West commands, which you already aware. Like you pass the -T option with, let's say, set of, let's say, RAM report, ROM report, or puncover, and additional utilities which you can pass, and then figure out what is the current layout of the memory which is being used. So when we pass to puncover, and then puncover reports this information saying, okay, so that's the top where you see the functions, wherein the code column space specifically says the code section size, which is totally fine, because like code section lives in execute in place, which is going to live in the flash, so which is not worried, so that's fine. So what we need to figure out is the static column when it comes to where does this set of 110 bytes of UART implementation goes. So these are not always going into the RAM section. I will explain that in a couple of slides later, but this also matters. But puncover doesn't work for this scenario, because when you have function pointers, which is the most cases in Zephyr, like any form of drivers, you have function pointers. So the data analysis within the function pointer is not captured as part of the puncover utility itself. When you say I2C transfer, and then the I2C transfer function have its some global data function variables, and then like there are variables which is defined within the function scope of that particular transfer function itself, those are not captured as part of puncover utility. So that means like we may not use this puncover utility to arrive at the final value where we can technically optimize it. So then what do we use? I mean, this is just an again example of a ROM report, but nothing to worry, because like ROM is totally fine in terms of the size. We have like around 16 kilobytes, or the SoC which we had like 8 kilobytes of flash. So this is just an example where you can see dash ROM report to see the size which is going to into the ROM or the flash itself. So here on the RAM note, you can pass dash, I mean, I'm not sure how many can see the screen. So dash C RAM report, where you can see where exactly, I mean, this is after the kconfig and device tree optimization size. So you might notice like 1226 instead of 1500, because this is a capture of, there are some more optimizations which is done on top to get it to that shape. And you can see these SWISR table, which is the software ISR table, which is captured for, let's say, dynamically generated from a Python script for all the IP peripherals like GPIO and UART and so on and so forth. But that 256 bytes is not going to reside within your flash, or it is not going to copy it into the RAM. That's a wrong report. There is a problem in, let's say, call it like RAM report doesn't identify this as part of RAM. Okay, so this goes basically to the flash and directly fetched from the flash, and that particular instruction is basically a const variable which is going to live in the flash region, not in the RAM region. Otherwise, you can see the kernel size itself is 117, which is the lowest possible configuration which we figured in terms of 1017 bytes for the kernel itself. And apart from which, you can see the clock, GPIO and all timers, which is the basic driver systems which we require to have some simple example working, let's say LED or hello world there. And there are a couple of other key important pieces which takes huge placeholder, let's say 112 and 256 for the stack, interrupt stack, and also for the main stack. So there are a set of things which is still missing in this slide. I will come to that in the later slide now. So before that, let's see what really goes into the final RAM section. So this is a simple representation. In the left, you see the flash, text data, auto data, and whatnot. You create, let's say, init sections and so on, all part of the flash when you flashed a new binary into it. And the right is the RAM section, where you have the data section, which is copied from the flash to the RAM during the initialization sequence. Means like very early initialization of the architecture portion, where you copy the data and as well as initialize the BSS to 0. So that's the portion which would be copied. And there are stack frame which lives in the and heap, if we really wanted to use heap in this lowest footprint. So what goes into that particular data section? So anything which you declare a static variable which is not constant, and you still modify that in your part of your program. For example, this snippet shows an UART data section which is part of the driver. The whole thing goes to the data. You can assume like if you're coming from a Linux world, you can assume like a process with, let's say, multiple threads. But then like the process is a single process system, as in Zephyr is a single flat hierarchy of memory. Once this data section is moved into .text section, data section, whether you use it or don't use it, it live for all the time of your whole booting sequence or the whole running time. So that part of memory needs to be super optimized so that like we can fit something or reduce the data section altogether. So when you declare something in static data or in global data that lives in the data section all the time, so that memory is totally gone. You cannot reclaim it if you don't want to use it or something like that. So that's one portion. And all the rest, let's say, for example, configurations which you mentioned for UART driver or any specific drivers, it's like const. So all of them goes directly into the RO data section. And during the execution phase, it's basically fetched from the flash itself. It's not like copied into the RAM section, so that's totally fine. Meaning, I mentioned about the ISR table, and that's also part of const, and it is part of our RO data, so we don't need to worry about it. So the only thing which we need to worry about is reduce the data section as much as possible to fit in something under 1024 bytes there. And this is a bit of an overview about what happens during the init sequence, because we need to see a way if we can run with multithreading or without multithreading, at least in the worst case scenario. That's like an overview about how normal boot sequence of an ARM system works, or ARM Cortex-M system works. So ROM code, from there you have a reset handler, and then from there you have an arc initialization specifically to do, let's say, initialize the stack pointer, initialize, let's say, MPUs and so on. And then you have an architecture independent portion of initialization in the kernel or init sequence of the kernel itself, which carries out like early init sequences in there, let's say kernel, post-kernel activities where the drivers is technically initialized. And then you have at least 3 threads in this equation when you have multi-threading enabled, which is dummy thread, main thread, and ideal. And when you don't have multi-threading enabled, that is straight away jump into the main function, and it's going to execute the main function in a loop or so. So there are 3 threads which I mentioned: dummy, main, and then like idle thread, which I will tell you what exactly that meant here. So dummy thread, you can simply assume it is a placeholder for init operation. During the init operation, before even the scheduler is initialized, before even multi-threading is really initialized, if there is an abort or let's say an exit failure, then the scheduler needs to know what can it schedule and look for the current pointer to the next list. And then idle is not there until this point. That means like it cannot derefer a null pointer. So that's why there is a placeholder called dummy thread, which is just like a safety net, you can call it, to avoid the null pointer exception in this. So this is a one dummy thread which is created but never been scheduled or never been used as part of the init sequences or any part of the system. But this lives in the target. So I will tell you why it's more important to speak about it in a moment. And the next thing is idle thread. Probably you might be aware, like when there is no task, I mean, all the scheduler is initialized and your functionality is running. And when there is no task to schedule, then the scheduler would eventually schedule the ideal thread, which would do power management and simply while looping, nothing much, but just power management and sleep the CPU. And the main thread by itself is like going to call your main function. From there, you would eventually see what additional things you wanted to do really under the hood for your application stack. So back to another memory analysis utility called pahole, which is also part of the VES system, which you can invoke -t pahole. The snippet which you see right above this is like there are 2 things which you can notice. One is the idle threads, and that's not the stack itself for the idle thread. Instead, it is actually the 112 bytes, which is for the threads metadata. When you wanted to create a thread, and this particular 112 byte is a global metadata maintained for each and every specific thread, so that like the scheduler can be aware of this thread and what to store within the thread context and so on. So that's why I said like when we have, I mean, you can notice like dummy thread is not part of it. We moved it away to save that 112 bytes to reduce the footprint in there. So this particular dummy thread is created in the init sequence, and it has never been used, even though idle is available after that the initialization is successful. So that means the 112 byte of dummy thread is been there, but never used in the data section. So it just be part of it all the time. So the way to get rid of it is either remove it, or a way to find that like still be available, but only do the early sequence of the initialization. So that's why I pointed out like 112 bytes of this metadata. I mean, that's like a minimalistic kconfig options which we chose. But if you have more kconfig options like debug informations and log informations being enabled for the stacks and so on, this 112 byte is like even more. It could be 1036 or let's say 1040, 148 and so on and so forth. So this is like the lowest footprint. So what goes into this 112 byte? Is there a way to reduce this? Unfortunately, no, because the largest consumer is this like the thread base and then the Kali saved registers, which is all part of the need for the scheduler, or when you wanted to have the scheduler to recover back to the previous thread, like this particular thread, then this information is mandatory. So you cannot cut strip this whole thing. The only thing is like you can remove certain unused portions of this data structure internally and then see if you can fit in that. So that's like thread-based structure, which is where you see the timeout structure, which is again pointing to the list of timeouts when you sleep. That is when it is used, and so on. So that's the memory layout POHOL on for each and every threads, which is like 112 bytes, which is gone for the lifetime. So if you wanted to create a thread, then like ideal thread or main thread, that 112 plus 112 is gone for the whole running of that particular system. Okay, then like what we did for the dummy thread to go away. There are two options. One, we completely removed it so that like we damn sure that like it is, there is no abort during the init sequences. That is one way. There is one other way, which is like enable the heap, and then like you could ask like what do we do with the heap, but I will tell you. But like with initialized heap and then free it once it is gone. So in the very early of C starting, this config multithreading has been creating this dummy thread. So the sections in between, let's say, why do we move a little lower in this path, meaning after the pre-kernel one? Because pre-kernel one is what initializes the metadata for the K heap, and then the heap itself is available. So we can create a memory and then use it dynamically and remove it only if there is a heap initialization is done. So we can either move the whole pre-kernel a little above, but then there is conflict in terms of device initialization on top as well. So this is the best placeholder. You can create a memory and then free it so that like we can save 112 bytes of that particular dummy thread structure. So that's how we get rid of, or let's say reduce 112 bytes of dummy thread there. With multiple other optimizations which I haven't posted in there, let's say removing various parts of the code inside the kernel, inside the init sequences, inside the data section, we finally managed to get it under, let's say, 1024 bytes, which is like 892 bytes right now. And then like, why not say now we are ready, we can change that fake value to 32 kilobytes to the actual 1 kilobyte size, and then try a simple, super simple example of this kind. So then like we started flashing it, and then what we observed is like, say, the hello world is printed and then the sleep never returned, meaning it was like there and it never returned. And then like we were trying to figure out what goes wrong. Like usually you have a multi-threading system, what would you can expect when you sleep, the interrupt should come and then it would wake back the scheduler and then like it technically reschedules this thread, right? So but then it never happened. What eventually resulted is like sysdig itself is missing in this particular SoC for some reason of you can say the size of the SoC, make it into a smaller silicon or so. They removed sysdig altogether in Cortex M0 Plus. In this there is no sysdig. So then how do we get, figure out, we still need multithreading. Without multithreading there is no use of running Zephyr. You can say, yeah, you can still run without multithreading and do a while loop of all the operations, but that's not the goal, right? So then we have to figure out what is the role of a system timer itself in any form of RTOS, including Zephyr as well. So there is a set of functionality which you can technically implement so that like you can replicate the purpose of sysdig in any form of hardware system. So what is that? So if you have a timer, you can configure and then implement these set of functions, make that timer itself as an interruptible system to the system timer, so that like you can configure this as a system timer and then like it can interrupt the scheduler as an input to this scheduler itself. So what it needs to be implemented, for example, the clock announcement for every tick. So that would be meaning like, say you announce every single tick, or when you have a power management enabled and sleep for, let's say, 10 milliseconds or 100 milliseconds, then you have to wake accordingly. So those part of implementation goes into sysclock announcement. So announcement by eventually means like it announces to the timekeeping system of the Zephyr, which is scheduler, and then there are set timeout and elapsed functionality, which would be the backend of, let's say, sleep functions, semaphore locks, and so on. So that part of it. So after we implemented this system timer, I mean, I think if you noticed, this is already done in the first screenshot which I showed in the RAM report. Basically, it includes the timer as well. So after doing this, we are managed to run hello world under the 24 kilobytes. And then in fact, like the system timer doesn't take any data section at all. So the same memory footprint, we managed to get the hello world in a loop. So that's a good thing. So that's a good success, at least in the first step. But that's not it, right? So you can blink an LED or a hello world, but that's not real application. But you can still say, oh, we still achieved, but nothing, it can be done. It's just a hobby thing. But what we wanted to do is something, let's say, I2C. That's the real purpose, because let's say this device can act as an I2C target or a controller in both mode or either mode. And then you can realistically say it can capture some ADC value and give it to the I2C controller, which is going to ask for a temperature or whatever the ADC sampling, which is done by this particular SoC, right? So then like we need to see if we can get some basic functionality out of I2C functionality in there. And we tried the de facto, which is done for the other MSP M0's I2C driver is ready. So then like we managed to try running this in this particular SoC. So what happened is like, we managed to fit it. I mean, I didn't put all of the other portions which we removed in the I2C driver, all of the other portions which we removed in the data sections to accommodate I2C as well as part of it. But we managed to put it under 1024 bytes with I2C functionally done. That worked, meaning like we managed to flash it. But then when we managed to flash it, it's the scan portion kickstarted. I mean, we cannot we cannot enable config shell and run an I2C scan, because shell itself is going to take, another 8 kilobytes, which is not going to work, right? So that's like we have to write a snippet of what actually scan does and then try running it. When you scan it, it's kickstarted. The device actually, there is a sensor which is living in 0x5, and which is in the other side, which is connected. But when we tried to do it, there was a transfer going, but then the other side basically acknowledges it, but nothing showed, and the system just like hang. There is nothing shown in the console. We could try enabling debug logs, but that wouldn't work because on the system is low footprint. So how do we figure out? So it turns out to be that like we saw the real kernel size is 117 bytes out of the compiled system. Even after all the optimization. So is it really 117 bytes? Unfortunately not. The reason is this. A simple example. So when you call a sleep function, or this is a simple example, right? Say when you call a sleep function, that would eventually trigger a tick sleep inside kernel. That would eventually call set of architectural dependent code to have locking, and then so that this thread can go to a wait state, and the next ready thread, which is probably idle thread, can be scheduled. So there are, this is a simple snippet. I can like put the whole UML sequence diagram. It would be like the scheduler would invoke at least 5 to 10 functions to figure out various other things that would be like recursive and so on and so forth. There is like plenty of function calls beneath it. And finally, the cswap itself is called in that same exact thread context. So which eventually means like swapping and running the scheduling, like simple algorithm, let's say the linked list algorithm or dump scheduler there, is running in the same thread context itself. So then eventually the problem itself is the stack is overrun. We were in an assumption to put the hello world to run under like 320 bytes or let's say 256 kilobytes of stack size for the main stack to work with. But that didn't work because basic sleep needs some amount of stack sizes to realistically work. Then what is that some amount? How do we figure out? So then like we've managed to do the stack analysis, because there is other ways to find the stack analysis in reality. Let's say there is a debug option in Zephyr where you can enable another thread in the debug system, subsystem of Zephyr, which you can periodically monitor each and every thread stack size, how large it can grow and so on and so forth. But then that option is not an option for us, because for that thread to run to debug other threads, that itself requires 2 kilobytes of stack size. So then like that wouldn't work, because we cannot run another thread just to monitor thread switches, and which is like a simple way, but then like still it is not possible. So then like how do we do it? So there is set of methods which is already part of Zephyr, where you enable set of stack canary. I'm not sure how many of you are aware of the stack canary methods, which is simply put, you have a stack of, let's say, 256 bytes. Before the thread basically been using this particular stack, the whole stack would be dumped with the same value, let's say 0xa, that is the default value, you can change it. So mem set to 0x for the whole 256 bytes. And then when you realistically call some function and try getting the size of the stack itself using the APIs, it would invoke and figure out how much of the stack you basically consumed until, let's say, where point the canary itself is the one which is set for mem setting this whole 256 bytes. So using that method, you can technically find which function takes how large of your stack sizes in the whole nutshell. So by which you can figure out, okay, how big is your sleep function, how big is your mutex lock function, how big is your mutex unlock function. So that's the outcome of this. Means like sleep needs 216 bytes of your stack, and then like mutex locks or mutex unlock technically require at least 248 bytes of your stack sizes. So that's how you arrive at what is the stack sizes which is really required in terms of running it. So after figuring this out, we have to squeeze even further to get this I2C scan functional and then make it working, because the stack sizes needs to be even more bigger, not just like 128 bytes or 256 bytes, that won't work. So we have to squeeze some more, meaning we removed plenty of other portions of the kernel code, plenty of other portions of the I2C driver, and then the data sections which is technically occupying there. And finally, we managed to get the I2C functional in a target mode to get it, let's say, scan functional and resultant of this device. So the evidence story is, this is a one real exciting path where we find what is the memory which is really needed when you realistically run in small footprint devices and how well you can optimize it. So during this path of this CX optimization, we managed to do plenty of other changes in the kernel, which is can, let's say, including the driver portions, but that's not yet upstreamed because there is in pipeline. I mean, if you notice, like all of them are like 4.0 or 4.1 Zephyr tree, which been currently downstream works, which is in the public still, but it's on downstream. We will clean up this and then probably send it to upstream sooner than later. So that's the idea. But then, like, as far as your maybe even if you're living in a luxury systems which is of 24 kilobits of RAM or 32 kilobits of RAM, so the best practice is always disable, have simple memory footprint. That's the best configuration which you can figure out in the nutshell. So that's it. Like otherwise, there are these effort of activities with snippets, samples, and everything is available in public. I think I haven't put in the public URL here. I would share that in a moment. But it's in GitHub public, so where you can evolve with those free sample PCBs and flash it. But just a quick note that like these PCBs are tested with, let's say, some minor hacking, meaning like it's not for friendly developers where you can just plug in the USB and play around. It won't be that easy, but it would be like you need to tinker a little bit more. That's mostly it. Yeah, otherwise, if maybe there is like 7 minutes left for the questions. Go ahead. Thank you. Any specific questions? Go on, please.
When you say you removed a lot of kernel code and driver stuff, how much of Zephyr was left at the end when you removed all these?
Good question. The question is to see after, repeat to the recording. So the question itself is how much of the code is left in Zephyr itself. So just to give a rough there, the kernel size was around 83 bytes after removal of most of those things there. And the I2C driver and all this were around less than 100 bytes. So that like we can fit in 1024 bytes altogether. So, I mean, like I can put all the screenshots of all the compilation things which we done, but the best is you look at the code and then feel about it. So that's the best, I would say, thing. I mean, there are, that's not a clean GitHub tree which we maintain because that's a downstream. We remove a set of things, play around, it wouldn't work, we revert. That's like a hacky way, yeah. Just go on.
Were you able to actually get a tickless timer, or did you have to just have, constant ticks?
Yeah, that's a good question. So right now we don't have a tickless timer out of it, but it is still possible to implement a tickless with the internal timer implementation, because like the set timeout and the elapsed portion idle exit is currently we are returning simply zero, just having from nothing in there. So tickless kernel is still possible there. Yeah. Yes, please.
Did you manage to actually sample ADC data and send it over SPC, or was the scan the end of the story?
No, no, scan is not the end of the story. So that's not going to be idle, right? So, I mean, the main motivation of this particular activity, you could think this is a hobby thing to do experiment, but it is not really a hobby, because MSP M0 has been currently used in plenty of places where also this. Beagle board organization creates this Linux-based boards where you have an EEPROM which is purchased from other vendors and which technically provides like 4 kilobytes of EEPROM or 8 kilobytes of EEPROM to storage. They interested in replacing this EEPROM with MSP M0 so that it can this particular IC can act as like I2C target, and then you can use the flash driver together and then store this 4 kilobytes. That means like one dependency less with the external silicon suppliers, right? So that means like we managed to get the flash driver running, we managed to get the ADC sampling running, and then able to get this ADC sample data. Meaning like you may not do the whole post processing of this ADC sample, because like that eventually require again a set of data sections, right? So we didn't do any manipulations of the data. So the raw ADC value would be sent. If you ask in the I2C, it would be sent over the I2C, so that like you mean the manipulation can be done in the host controller, which is maybe luxury to live with. So flash controller is working, I2C target mode is working. You can say controller mode is working, but then like what do you do with the controller of this size is no, right? So I2C target is working and ADC is functional. So that's the portion. There are other portions which we could try like PWM and other things, but I don't know what is the real use cases which would come. Yes, go on. Yeah, that's the point. We have a, I don't know, like if I can pipeline it, show it, then. Let me see if I can show it. This is the, downstream fork, which we keep it here for internally. So let's say MSP M0, there's CX. So that's the downstream version, which is based on CX 4.0 version. But as I said, we have a collaboration with Texas Instruments at this point of time to get their MSP M0 series completely upstream, and we are doing it internally. Like, I mean, part of it is already available. Means like there is a strong pipeline which is upcoming for the upstream, and CX is also included. So yeah, like we're trying to do it. That's the hardest part to push it into the Zephyr tree, because like drivers and other things would be specific SoC things that we can do manage it. But with respect to the kernel, with respect to the initialization sequences, we can push this optimization, but this must be acceptable for all the other SoCs, because that's like a Cortex M series which we are killing it, or yeah, try. Yeah, that's a good option to do. But I mean, like, yeah, the way we removed plenty of this scheduler portions as well. Meaning, like in the dump scheduler, we reduce various pieces. So Andy Ross, like, I'm not sure if he's here, like, how happy he would be in terms of accepting those into the scheduler itself. I mean, like, the idea is to push into the upstream. I mean, either it is acceptable or not acceptable, to try to lean around and see we can, come into a common ground to upstream, but either will be completely manageable to upstream it. We will try it for sure in the coming days or coming weeks, you can say. Yeah, sure. I mean, keeping it downstream for the super long run is not our part of our goal of the company. We primarily focus on open source. Yeah, we will do it for sure. There is, I think, one more minute left. Any other further questions? Yes, go on, please. Yeah, that's example which I showed you. Told you like the real consumer of this SoC itself. I mean, I don't know what is the idea of Texas Instruments being launching this small SoC in a nutshell, but I mean, just an assumption would be is to have a placeholder, you can say crossover between your 8-bit, 16-bit, and then crossover between your 32-bit with sticking with 32-bit. But you can use it as an EEPROM, I2C sensor or something like that. Yeah, please go on, David.
Separating the use case for the chip, I'll comment that one of the most valuable aspects of Zephyr is its driver model,
Yeah.
right? So if you can get this running on something like that, then you don't have to do bare metal drivers and a different programming model. And so for programmers, you can do an application, it's writing to the driver, the Zephyr driver model, then that application can be easily ported to the scaled up version of that potentially as you add to it, but it keeps a very common programming model across the whole line of chips. So that's why this is super interesting.
Yeah, super valid point. In terms of when you create an application of this different scaling, you don't need to worry about, let's say, how do you speak with the sensor, how do you speak with the I2C driver. You don't need to write every time the same thing because the model itself, the I2C model or the driver model itself will help you doing that. Yeah.
I mean, because you could even go one more step further on this, get rid of the multi-threading. You still have driver model available to you at that point.
Yeah, adding to the point, when we disable multi-threading, which were around like 700, 660 bytes around. So when you disable multi-threading, it's super low because we don't have the kernel scheduler portions in it portions. So with 650 bytes gone and then like around 400 bytes, you can play around with application. That would be a plenty of playground you can still make.